hope you have all seen many Schwarzenegger movies. So you're familiar with the Germanic accent because, as Corey mentioned, I'm German originally, and I'm told that I have a heavy German accent. So feel free to interrupt if you have questions, if you don't understand me. And obviously we can have a bunch of questions after the talk as well. I want to talk about volcanogenic massive sulfide deposits and specifically about some of the ideas how we can explore for this important deposit type using geological criteria. So just to remind you what we are talking about, VMS deposits, volcanogenic massive sulfide deposits, are sulfide accumulations that have formed at an ancient seafloor. More specifically at the seafloor or immediately below the seafloor, and I will comment on that in some more detail today. There has to be a spatial and temporal and typically a genetic association with volcanism, which is obviously the reason why we refer to these deposits as volcanogenic massive sulfides. In fact, the deposits vary in style. Obviously, we care about the massive sulfide lenses that you're all familiar with from the literature, or many of you have probably seen these deposits before. But in many cases, we also mine discordant zones of veins that we refer to as stringer zones, or in some cases, we today even care about disseminated zones of ore that especially have elevated precious metal contents. Obviously, VMS deposits are polymetallic, which helps us in terms of the economy. The volcanogenic massive sulfide deposits range in age from really old, with some of the best examples in the ancient rocks of the Western Australian Pilbara block ranging as far back as 3.56 billion years to the modern seafloor. And as Corey mentioned, I've been fortunate enough to work on some of the old rocks, mostly the Archean rocks in the Abitibi Greenstone Belt in Canada, which is about 2.7 billion years old, all the way to the really young deposits on the modern seafloor, giving me some perspective on how these deposits form. We obviously have extracted some of these deposits for a couple thousand years. You know, some of these deposits in Cyprus are amongst the earliest producers of copper in human history. The Rio Tinto deposit that you have all heard about, and obviously the company Rio Tinto being named after it, has been in production for almost 2.5 centuries. However, we also know that these deposits occur on the modern seafloor, and that was discovered in 1978. The modern seafloor occurrences were discovered in 1978 by a French submersible cruise, and then shortly after that revisited by the submersible Alvin, which is an American submersible that you can see in the right-hand image there in 1979. The dive by submersible Alvin really discovered the hot springs on the seafloor that you can see on the left-hand side, the black smokers where we have the emission of this hot aqueous fluid up to almost 400 degrees C at the seafloor, getting quenched very rapidly and precipitating these little particles of sulfides in the smoke as the black smokers as we know them today. This was a huge change in terms of our understanding of VMS deposits. Huge amount of research have been conducted since basically 1979. Not so much because we care about the economic geology or how these deposits form, but mostly because of their biology implications. As you can see on this cover picture there of Science, which obviously is an important research journal, there are chemosynthetic fauna that are living down there on the ocean floor, and they are essentially eating up the H2S that is coming out of these vents, and the bacteria that are sitting within the stomach of these different animal species are using the H2S to produce sugar, and then these other organisms like tube worms and crabs and so on use the sugar to live. So these are chemosynthetic vent communities. They are on the deep oceans where we have no sunlight, and that was a huge revelation when we discovered these, basically in the starting in 1979. Very early on, we understood that that could be possibly the origin of life. And obviously that has created a lot of interest in these hot smokers on the seafloor. By today, we know of about 350 of these sites on the modern seafloor. You can see a compilation of those locations on the world map there. And they are really occurring in quite diverse settings. That includes a lot of black smoker systems on mid-ocean ridges. Those are the locations where they were discovered in 1979, 21 degrees north on the East Pacific Rise, a mid-ocean ridge. But in the last almost 20 years or so, a lot of research has focused on the arc environment. We today know that VMS deposits, or their modern equivalents on the seafloor, also form in arc environments. Down in the lower left, you can see an example of a compilation of these different modern seafloor systems and the tectonic setting of the 350 deposits, or occurrences, I should say, that we know of today. Obviously, still about 50% of those are on the mid-ocean ridges because they have been very well explored. But by now, we know about 15% of these are located in arcs, or about 10% in rifted arcs, and about 20% in back arc rifts. These are, in fact, the settings that we care about when we talk about the ancient systems, right? When we compare the geological setting of the ancient VMS deposits to the modern seafloor, we really have to go to these arc-related systems, because, as you know, mid-ocean ridges, very interesting, but ultimately they all get subducted, right? The chance of preservation of VMS occurrence on oceanic plate is really slim if we are in a mid-ocean ridge environment. Now, because we have obviously mined VMS deposits basically since day one in locations like Cyprus, and we have studied them extensively in the ancient rock record, and now we know how they form on the modern seafloor, we obviously understand the VMS systems very well. This led to this very famous statement by Brian Skinner, obviously one of the foremost economic geologists, that the VMS system really is probably the best understood mineralizing system we have today. And I certainly totally concur with that. Within the VMS world, we do understand the ore deposit system very well. Aside of that, probably low sulfidation epithermal systems are the next runner-up, because we do have those deposits, but we also understand how modern geothermal systems work and how mineral precipitation occurs from geothermal liquids. But really, the VMS world are amongst the best understood mineralizing systems. So I want to talk about that a little bit, and also update you on some of the research that was conducted maybe over the last 15 or 20 years, which in fact has shifted our understanding of the VMS world to some degree. So let's think about the geological setting, because we do want to talk about geological exploration implications. So first of all, obviously, when I got into the VMS research, everything we ever thought about VMS was kind of derived from our understanding of modern seafloor systems in mid-ocean ridges, which really is not the best example. It's not a correct example of where these deposits form. Today, this is quite different, and we understand, obviously, as I mentioned before, that the ancient deposits formed in supersubduction settings. Here's an example, the Funuli Rift. This is in the lower basin. This is the northern part of the lower basin. You can see a volcanic chain here. This is an arc volcanic chain in the Pacific. Tonga is up here, and this is the Tonga Kermadec Arc. And there's subduction from your right-hand side to your left-hand side, forming an extensional basin, the lower basin behind this arc. The extension is very complicated. There is a triple junction up here and some extensional ridges, back arc spreading centers where a new crust is created, as you can see with these lines. And along these lines are a number of hydrothermal systems that are given in the red dots and the yellow dots. However, if you follow, I don't know if you can see my cursor, but if you follow to the south where it says Funuli Rift, if you go all the way down here to the south, you can see how that rifting actually extends into the arc, right? Which is kind of interesting because the rifting up here, it's spreading, but then it becomes a rift zone, is oblique at an oblique angle to the arc, and then actually splits the arc. That obviously is related to the subduction angle relative to the arc front. So up here is a 3D visualization of what the bathymetry, the depth profile in the ocean looks like, and you can see the Fumuli rift, a little volcano in the rift, and that's where one of the large vent sites is located on the modern seafloor at about 1,555 meter water depth. There's a bunch of these black smoker chimneys, some of which are in the order of about 20 to 30 meters in height, really large black smoker chimneys. So today we know that this could be a good example of the setting in which we make these ancient deposits, rifting in arcs. So in fact, Rodney Allen in 2002, he compiled data for ancient VMS camps worldwide and essentially came up with this idea or this concept of the tectonic setting in which these ancient VMS deposits must have formed. So what we understand from this compilation that Rodney Allen was leading at the time is that VMS really form in zones of intense crustal extension. This is in a supra-subduction environment. So on your right-hand side, we would have a downgoing slab, an oceanic plate, getting subducted. Then we have an overriding plate, and you can see an andesitic volcano there as an arc, as the arc front. And then maybe behind the arc or within the arc, we would have intense crustal extension in an anomalous period of extension for, maybe because we have slab rollback, which causes extension in the arc or behind the arc. We obviously also can have extension in the front of the arc. However, that typically does not form VMS because of heat flow constraints. If you have extension in front of the arc, we're not producing a lot of melt. That means we're not producing a lot of heat sources for our hydrothermal systems. So typically we have to have extension in the arc or behind the arc. So that's what you can see there. Extension behind the arc by slab rollback. That means we are decompressing the mantle as we are thinning the overriding plate. We are producing a lot of mantle melts, and these will initially get stuck in the overriding plate and produce crustal melts. As we continue this rapid extension for maybe, let's say, 1 million years or about 2 million years, eventually we will have some of these mantle melts getting all the way to the seafloor of the overriding plate. So initially we produce mostly partial melts in the overriding plate, and eventually the crust is so much thinned that we can have these basaltic melts, these mafic melts getting all the way to the seafloor, typically resulting in these fissure fat eruptions. This is what we call the VMS stage. So within any given extensional environment, where we do form VMS, there's this magic VMS stage, a period of time that is about 1 to 2 million years after the onset of extension, during which most of the VMS are made. They're obviously not necessarily made all at the same time, and we'll talk about that, but within a short period of time when we have this pronounced, very rapid extension. And we can see that worldwide if you look at VMS camps. Here's an example of northern Queensland, the so-called Mount Windsor volcanic belt, which is Cambrian to lower Ordovician in age. And essentially a stratigraphic column through this would look about like that. We have a lower succession, which is called the Puddler Creek Formation, that is mostly made out of sedimentary rocks and some continentally derived clastic material, which is kind of the passive margin stage material. Then we go into rapid extension and we start to melt the overriding crust, and we produce a lot of massive felsic magmas, which give us the Mount Windsor Formation. That's about 3.5 kilometers in stratigraphic thickness, all felsic volcanic rocks. Think about rhyolite domes and lavas, and related autoclastic breccia. Now suddenly we start to get mantle-derived melts to the seafloor. So we really have bimodal volcanism. We have basaltic and rhyolitic lavas at the same time, with the basalts ultimately being derived from the mantle melts, and the rhyolites being derived from partial melting of the overriding crust. That gives us what we call the Trooper Creek Formation in the Mount Windsor volcanic belt, about 4 kilometers in thickness. All of the VMS deposits, including the largest deposits, referred to as the Selenga deposit, are located in this bimodal volcanic succession. Then extension stopped, and we basically had just shedding of sandstones and mudstones from the nearby topographic heights into that basin. And there's really very little or no volcanism anymore, which means there's also no VMS, because VMS are spatially, temporally, and genetically related to volcanism. So as a very first approximation, you can see that in any given volcanic belt, there are certain parts of the volcanic belts that are better for VMS than others. In this particular case, it's the bimodal volcanic succession that is most interesting. And that's really what we see in many camps worldwide. There's obviously always exceptions, but as a rule of thumb, that's something we can see worldwide. It's the approximately contemporaneous emplacement of felsic and mafic melts at the mine scale or at the camp scale. Here's an example from Kidd Creek. Kidd Creek in Ontario obviously is one of the most world famous VMS deposits, contained about 140 million tons of massive sulfides and sulfide stringers and some disseminated sulfides at an average grade of about 2.3% copper, a little bit over 6% zinc. It's Archean in age. You can see a stratigraphic column, a simplified stratigraphic column. There are footwall volcanic rocks. These are komatiites, ultramafic rocks. And then on top of that, we have a pretty thick succession, about 300 meters or so, of coherent and massive rhyolites and related orthobrachia. Then we have volcanic clastic rocks that are felsic in nature. And then we rapidly change into mafic volcanic rocks. Some of these are intrusive in nature. Some of these are extrusive in nature. And our VMS deposits, multiple lenses at Kidd Creek, are sitting right here in this bimodal volcanic succession. Another example is SK Creek. I'm sure you have heard the name SK Creek before as being a world famous deposit because of its high gold content. It is the deposit, VMS deposit, with the highest gold and silver concentrations that we have. If you have followed the press releases and things like that, SK Creek will probably get a second life now, with Skeena Resources looking at it to reopen SK Creek. Again, very interesting because the deposit is located in a bimodal volcanic succession. Here are drill core logs that I made a number of years ago when this was still a barrack operation. You can see that in the stratigraphic footwall in red, we have rhyolite units. These are very complicated. Some of these are massive lavas. Some of these are more like domes. A lot of these lavas are brachiated through cooling and autobrachiation. Some of these lavas, rhyolite lavas, are intrusive. Some of these have been redeposited as volcanic clastic material. They are overlain by carbonaceous mudstone. And in fact, we can see locally intrusions of the rhyolite into the carbonaceous mudstone. There is a volcanic texture that we refer to as peporites, which show us that the rhyolites have been intruded into the mudstone when the mudstone was still wet and unconsolidated. So these are specific volcanic textures that allow us to see that the clastic material, the carbonaceous mudstone, was still wet, which means it contained water, unconsolidated, which means it's very young. So that means that the mudstone was deposited and we must have intruded the rhyolite pretty much right away. Then we have the massive sulfides, and many of these massive sulfide lenses, in fact, are clastic in nature and have been transported over short distances. And then within the hanging wall, mostly in the hanging wall of these massive sulfide lenses, we have mafic units. And these mafic units, again, are mostly intrusions, sills and dikes, mostly as a sill and dike complex. And again, they form these papyritic margins, which means, again, they have been emplaced into the mudstone when the mudstone was wet and unconsolidated. So that means that really the rhyolite and the basalt, the rhyolite in the footwall and the basalt in the hanging wall, we are pretty much in the same time slice, right? They have not been formed over millions of years. We are talking about something like 50,000 years or 100,000 years, when the host rock, the carbonaceous host rock, was still wet and unconsolidated. Again, evidence for contemporaneous emplacement of felsic and mafic melts. Here's some other examples of what kind of volcanic textures we can see to prove that mafic and felsic magmas have been in place at about the same time. This is from Cuimont, a very large gold-rich deposit, VMS deposit in the Noranda camp, the world famous Noranda camp in the Archean Greenstone Belt, the Abitibi Greenstone Belt in Quebec. You can see a surface map with a bunch of dikes, and again, the felsic dikes are on these kind of orange and reddish colors, the mafic dikes being in the green colors. And you can see this fancy relationship here between this mafic dike and the felsic dike, and all these little kind of enclaves and little droplets of the mafic material in the felsic dike. And this is as evidence for magma mingling and mixing. So these are mingled, they are basically emplaced, both magmas have been emplaced at the same time. So along one volcanic structure, we had emplacement of essentially a batch of felsic magma at the same time as we had emplacement of mafic magma, and then these were mingling. If we would do a geochemical profile across the felsic unit here, we can actually see that it becomes more felsic as we go away from the contact. So there's also geochemical mixing of those two magmas occurring along the contact, which again means both magmas had to be emplaced at about the same time. Here's another example of the same kind of relationship. This is the world famous Horn deposit. This is about 53 million tons at about 6 grams per ton gold and some copper, historic producer. Also, there's a significant resource left at depth. Again, here's a surface map, and you can see essentially a section, the stratigraphy is steeply dipping, a section through a dome. And when we look at this felsic dome, right, this is a rhyolite dome. When we look at the rhyolite dome, we can find these clasts, these xenoliths of mafic material floating within the felsic dome. And the flow foliation of the felsic material surrounds that clast. The clast is really funky in shape. You can see these scalloped surfaces. This was basically a melt droplet that was incorporated into the felsic magma. So again, this is evidence for magma mingling, contemporaneous emplacement of mafic and felsic magma. That's our bimodal volcanism that happens in these strongly extensional zones. Okay, so let's zoom in. We have rift zones in a suprasubduction environment. That's kind of what I was getting at, that are rifting and extending very rapidly. Now we have the VMS stage, which means we have the perfect conditions to make VMS deposits. And then if we look at these camps worldwide, in most of these camps worldwide, there are what we call favorable horizons. There are certain locations in the volcanic stratigraphy that are better than others. In many camps, there is one favorable horizon or maybe two. In some camps, there are more than that. Here's an example, the Noranda camp, which is obviously one of the best studied camps, VMS camps we have, where the stratigraphy is very, very well known from both academic studies, decades of academic studies and exploration work. Harold Gibson, who is now at Laurentian University, has spent much of his life mapping this camp at the scale of 1 to 2,000. So this camp is studied in great detail, and we compiled this diagram for publication in 2017 that shows you the distribution of these VMS deposits. Those are all these red dots here within the volcanic stratigraphy. And let's not worry too much about all these different names and complications, but essentially what you can see is a bimodal volcanic succession with mafic rocks in green and felsic rocks in the pinkish and yellowish colors, and then the distribution of the VMS deposits within the camp, going from north to south and from stratigraphic footwall to hanging wall. You can see that many of these deposits occur along particular horizons, thin units within that extensional zone. So the entire camp is an extensional zone, a rift zone of some sort. And then within that rift, within this extensional zone, we obviously don't really know what its 3D structure is. That's why it's just called a subsidence structure. Within that zone of strong extension, there are certain periods of time when we have made VMS deposits. More at certain levels within the stratigraphy at these favorable horizons. This was in fact recognized very early on in the exploration, and then explorationists obviously tried to chase down these favorable horizons and drilled them at very close patterns to find all of these different deposits. And then suddenly somebody recognized that there's another horizon further down in the stratigraphy, which resulted in the next exploration boom and so on. But you can see how important it would be to recognize these horizons. They are not simple to recognize. In the Norenda camp, we are talking about very thin marker units that are carbonaceous mudstones, shales, or we call them tuffaceous units, or contact tuffs, that are about 10 centimeters in thickness. And you have to chase these throughout the volcanic stratigraphy, throughout the camp, to find these favorable horizons. So it's a geological challenge, and that's why we needed a lot of detailed mapping and a lot of good drilling and very fantastic geologists to find these favorable horizons and to trace them throughout the camps. But then VMS exploration is a bit like mushroom hunting. So if you have found one of them on a favorable horizon, there's typically more than one, and there are more nearby. And there's still exploration ongoing in the Norenda camp after, a little bit over 100 years of exploration, with more deposits being found on the same horizons. If we go to the modern seafloor, we could obviously study these horizons because essentially the modern seafloor is that horizon, right? So if we would have a bunch of little black smoker systems on the modern seafloor in different locations within one extensional zone, that is our favorable horizon, right? We are on one time slice. We are in the year 2020. That's one time slice in the extension of one of these basins. So let's go to the Manus Basin here in Papua New Guinea, in the eastern Manus Basin. It is very famous because we have rifting extension in all the arc crust. And you can see these volcanic ridges here that are kind of northeastern striking. And all of these are volcanic ridges that are formed by seafloor volcanism that happen as a result of this strong extension. And we have all these black smoker systems located throughout the basin. So this is one time slice, right, today, one favorable horizon. And there's a bunch of these VMS occurrences. Now, what do we see here? Well, it's a big place, right? This is one big basin with a bunch of VMS occurrences on one time slice. And surprisingly, this map is a bathymetric map, so it shows you depth. The deeper it is, the darker the color, the colder the color, the shallower it is, the hotter the color. As you can see, all these occurrences are located at topographic heights. So very counterintuitive, because we always think about extension as being a basin. That's true in the big picture. But within those extensional zones, we have seafloor volcanism, and the VMS are located in spatial, temporal, and genetic relationship to seafloor volcanism. And seafloor volcanism makes topographic highs. That means our VMS are located on topographic highs. And that's exactly what you see here. All of these hydrothermal sites are on topographic highs within an extensional zone, which obviously is a topographic low overall. Now, here's a very famous diagram from Ray Binns in 2004. He published this as to show us how dramatic the topography on this favorable horizon, the today's seafloor, could be. Right. So here's the today's seafloor, the topography of today's seafloor, the elevation of today's seafloor, which is obviously measured. And then he just put a bunch of volcanic rocks on top of it. You know, those are obviously invented because they haven't erupted yet, to show us what this is going to look like in an ancient volcanic succession prior to any kind of deformation. Right? So this would be an undeformed volcanic succession with the topography being the topography from the modern seafloor. This is a scale of 10 kilometers. This is Pual Ridge, which hosts the Pacmanus hydrothermal site, which is the largest site in this location. Have a look how crazy the topography is. We basically go a kilometer up and we go a kilometer down. So think about the exploration implications of that. A topography difference of a kilometer of, you know, over maybe a distance of 5 kilometers or something like that. You know, what does that tell you about drilling patterns and so on? And these are obviously, this is fictional in an undeformed volcanic succession. You know, talking about seafloor relief, here is another example from the Manus Basin, where we have a bunch of little VMS occurrences sitting on the modern seafloor on a string of dayside domes. So again, this is a bathymetric map. Hot colors is shallower, cold colors is deeper. You can see the trace of these domes of daysides sitting on a plane of more mafic rocks. Then here are all our little sulfide occurrences, and the water depth is given here. You can see Solvara 1, which is at the center of two volcanic structures that are controlling the emplacement of these volcanic rocks. And Solvara 1 is located at a depth of about 1,600 meters or so. And then we go up the dome to North Sioux, and North Sioux is at 1,200 meters. So that's 400 meters difference in elevation over as little as a kilometer and a half. Right now, think again about what that means for drilling patterns, how far you have to step out, a kilometer and a half, and your favorable horizon would go up by 400 meters, right? So on the modern seafloor, there's nothing like horizontal sedimentary basin kind of things. So when I go out with students and we look at volcanic successions, they obviously all come from CSM, and they all have the Denver Basin in their mind where everything is flat. That's not true in volcanic successions, right? I think that's the biggest takeaway message from working on the modern seafloor. There's nothing like a flat seafloor. Like everything has strong topography controls. In fact, Solvara 1 is the only true deposit on the modern seafloor that has been drilled and has an indicated and inferred resource on it. And you can see those numbers there. You know, another example of the same kind of idea of topography is the Thalanga deposit in the Mount Windsor subprovince in Queensland, and I mentioned that before. Again, we can see a volcanic ridge here with the massive sulfide located on the topographic high, not on the surrounding topographic low, which are the mafic volcanic rocks that make a plain. Same thing in Japan. Here's an example from the Hokuroku district that Rodney Allen studied in great detail. This is the volcanic stratigraphy, and you can see the favorable horizon going all the way up here on top of the deposit. You know, the deposits are here. These are all volcanic rocks that are altered. And then it suddenly dips down here on this hole that's called HO65 and goes down slope, and then it's down here, right? And there's a scale for reference. We are dropping down by a couple hundred meters over, you know, something like 500 meters distance. These are on the right-hand side are all volcanic rocks that are younger and hydrothermally unaltered. Again, what would that mean for you if you're drilling up here? You know, up here you drill a hole and you get into massive sulfides, you know, over maybe 200 meters drill hole length. And then if you would step over here and you only drill 200 meters, you never get out of unaltered volcanic rocks because you are far on the hanging wall. You know, as I said, volcanic bedding in volcanic terrains is not horizontal. Here's a seafloor image from the modern seafloor. Look at the angle on that bedding, right? So think about that if you're out there with your Brunton compass in volcanic successions and you put that on a bedding and you think the bedding is flat, well, think again, right? This is something like 30 degrees, very close to the angle of repulsion, right? If this would be a little steeper, obviously would collapse and slide down the hill. You know, when we did a lot of the seafloor exploration, you know, 30, almost 40 years ago, one thing that was striking is in what kind of water depths VMS occurrences were located on mid-ocean ridges. Obviously, most mid-ocean ridges are very deep in terms of water depth. You know, think about something like 2.5 kilometers to, in some extreme cases, as much as 7.5 kilometers. So our idea has always been that VMS have to be very deep marine, and that's probably still very much appropriate. However, whether they're always quite that deep is a different question, because in subduction environments, we are typically not quite as deep. However, we know for sure that VMS deposits are not in shallow marine environments. And VMS deposits are not formed in really shallow environments like the one that is shown there, where we have storm wave action, huge waves that would go all the way to the seafloor and then rework the material at the base of the seafloor. Out of the about 800 deposits that Jim Franklin has compiled for the 2005 review paper on VMS deposits, which is the last big compilation on VMS deposits, there are probably 2 or 3 deposits where we have erosional evidence for erosion within the volcanic successions, immediately above or below the VMS deposits. Their significance is still very much under debate, but overall, you know, out of these 800 deposits, there's really almost no question that we have to be below 200-meter water depths to make it work. There's also geochemical evidence for that. It's almost unthinkable that we could transport copper at low temperatures. Copper is typically transported in these types of hydrothermal fluids at temperatures well exceeding about 275 degrees C. We know today that there is a control on the maximum temperature that hydrothermal fluids can have that is imposed by the boiling curve, and that's something you may have heard from the epithermal environment as well. If you would have a liquid coming from depth, it will start to undergo phase separation, boiling when it hits the boiling curve. When that liquid produces vapor, it will cool very rapidly because it takes energy to make vapor. It's not possible to get in an open system to really low pressures, shallow water depths at high temperatures. So here is a compilation of all the vent temperatures of seafloor hydrothermal systems on the modern seafloor. And you can see that they all plot into the liquid field or right on the 2-phase boundary, but there are no hydrothermal systems out here. That is just not feasible. It's just not possible. In fact, that's one of the ways that I usually win a case of beer or something like this on a research cruise, because we can go there and then obviously we'll eventually find some black smokers, maybe if we get lucky. And then when we have discovered the black smokers, we obviously know what the water depth is, because we can measure that from the ship by echo sounding, or we have a tool that goes down, takes pictures, and then we know how deep that tool is. Then we can go and look at the boiling curve. And since we know the water depth, we can obviously read off the temperature, the maximum temperature of those liquids. And then I usually make a bet with any of the sailmen, you know, the captain or whatever who goes for a bet, and tell them, well, if we're going to stick a thermometer into the black smoker, the maximum temperature is going to be 325.5 degrees C. And they think I'm crazy, because how could you ever possibly know? And then it's exactly that, right? So this is basic thermodynamics. In an open system, we cannot have temperatures that exceed the temperature of the boiling curve at a given depth. That's for sure a case of beer if somebody goes for that bet with you. Well, that means, I guess that means we cannot really be in shallow marine environments like 200 meters or 300 meters and have temperatures that are high enough to transport copper, right? So that's not really possible. In fact, I've worked on one of the shallowest black smoker systems that is out there. This is Offshore Panorama in Italy, which is a really beautiful place to do research. Lots of great sushi. You know, it's obviously in Italy, so it has good wine. And you can scuba dive to about 23.5 meter water depth and find the shallowest black smoker system in the world, which is this little guy, and scrape off some of the sulfide precipitates, and there are no copper minerals at all. These are sphalerite and galena and amorphous silica and some sulfur salts, but there really is no copper transport whatsoever because the vent temperature of that liquid is at 110 degrees C, which is just about the boiling temperature because it's so shallow. The pressure is so low, just so much slightly higher than what you obviously have at 1 atmosphere. So we cannot really make a polymetallic deposit that is copper rich in shallow water. So that means we still have to have VMS formed in deeper water conditions. So we have to be in an extensional setting, rapid extension. We have to have a favorable horizon and one or more favorable horizons. And the favorable horizons have to be in a minimum water depth of, let's say, about 500 meters, probably more realistic, 1.5 kilometers and more, right? If you are too shallow, there's really no chance to have a copper-rich VMS deposit. There's a lot of scientific debate on whether we could have gold enrichment without copper, but I'm not going to go into that today. Then I guess the next question is, where on the favorable horizon do we have to go? Right, so the favorable horizon, think about the Noranda camp, goes through the entire camp. But the deposits are not everywhere on that horizon. So in 2D on that plane, where exactly do we have to go? And clearly this is going to be controlled by synvolcanic structures. We have to bring our hydrothermal fluids, the high temperature liquids, to the seafloor, and that has to be structurally controlled. So here an example from the Noranda camp. There's 2 sets of structures. There's one fault that has controlled the string of domes, and there's another set of faults at high angle. And where these 2 faults are intersecting, that's where the highest permeability is, the most fluid flow, with the largest deposit, the Millenbach deposit. So the structures are key. They will control the fluid flow, but they will also control where exactly the seafloor volcanism occurs. So here's another example from the modern seafloor. Again, a bathymetric map. Hot colors is shallow, 2,104, to cold colors, 2,163 meters. So this is about 60 meters difference. And you can see these faults here, extensional faults, and you can see the fault scarps and the location of the vent fields, which are given in these squares. Right? This is a very high resolution bathymetric survey. And you can see that these sulfide occurrences are in the structural hanging wall of these extensional faults or right along the faults. The faults control the fluid flow. There's just no question about that. We can really pick any VMS deposit you want to, and we will see a strong structural control on where the ore lenses are. However, I should say typically it's very difficult to identify synvolcanic structures because, well, they are in altered rocks, they have been reactivated, they have been used by younger volcanic processes and infilled with dikes and sills. So they're not always very simple to pick in the field. However, we always have synvolcanic structures controlling where the sulfides are in detail. Here an example, the Laurent District deposit, a world-class gold-rich deposit, and it's still the #2 gold-rich VMS deposit. My very close colleague, Patrick Mercier-Langevin, in Quebec has worked on this forever. I have worked on the Horn deposit in Noranda, which is not very far away, about 45 minutes. And every time we meet, we are kind of looking at the latest statistics to figure out whether Laurent has caught up with, in terms of gold production, with Horn, because Horn is a past producer, but Laurent is still in production. So Laurent is probably going to be the biggest gold-rich VMS deposit eventually, sooner or later, because it's still expanding in terms of size. Look at the numbers, almost 80 million tons at almost 4 grams per ton. This is 9.3 million ounces of gold in the VMS deposit. And there's very little other stuff. Right? There's a little bit copper, and there's a little bit zinc, and a little bit lead. So really it's a gold deposit if it comes to it. And then the copper and the zinc and the lead pay for the operation. This is a fantastic gold deposit because it's producing at a negative cost, right? Because everything is paid for by the base metals. However, if you look at that, the ore lens, this is the distribution of gold. The location of the ore lens is very strongly controlled by the volcanic structure here. There's a parallel structure that controls another deposit called Dumagami over here. So these volcanic structures are controlling where the sulfides are forming. I also said that the structures control where the seafloor volcanism is. Because obviously the lavas have to get to the seafloor, right? There's going to be a subsea floor volcanic intrusion. And then these magmas and lavas have to get to the seafloor and vent on the seafloor, and that's going to be structurally controlled. So VMS deposits form in spatial, temporal, and genetic association with seafloor volcanism. They are what we call vent proximal. They are right next to a volcanic vent. And that is really one of the big keys in VMS exploration. We can vector towards a VMS deposit based on volcanological evidence, whether we are on a vent proximal, intermediate, or distal environment. If we are way away from a volcanic vent, it's hopeless. There's never going to be a VMS deposit. If we are getting closer, we will see more massive lavas, coherent lavas, more breccias, fewer volcanic clastic rocks. We'll see more dikes and more silts, things like that. So it's key to look for the vent proximal fascias. So just to give you an example, a beautiful, really, really important study by Rodney Allen that was published in 1996. He was originally a volcanologist, then went into economic geology and eventually became the VP exploration for Boliden. And he worked in the Skellefteå district for, I think almost 25 years or something like this. And he basically remapped much of the Skellefteå district with his team to figure out what the volcanological setting of all these VMS deposits is. The Skellefteå district is about 1.8, 1.9 billion years old. By now, they have discovered about a little bit over 50 deposits. And you can see the location of the deposits with respect to these volcanic centers schematically here for 2 of these clusters of deposits. The deposits being the red massive sulfide lenses, and they're always proximal to these felsic volcanic intrusions and domes and lava flows. Down here is a scale that shows you what's proximal, medial, and distal. So on the scale of 1 kilometer or 2, we can zoom, we can vector towards the massive sulfide lenses. Right? This is really important because VMS deposits are small, they are massive sulfides, they have a high density. So to have a couple million ton deposit is really small. If I look at Berthold Hall as a building, that's 500,000 tons of massive sulfides, if it would be massive sulfides. That is really a small volume for a pretty nice endowment of metals. So being able to vector towards these small massive sulfide lenses using geological criteria is key. Here another example from the Flin Flon district, Flin Flon deposit in Manitoba. Harold Gibson worked there for almost 20 years. And it shows you the location of Flin Flon and 777, and then a more recent discovery, the Cullinan deposit. And they all together are about 100 million tons with respect to one of these felsic domes. And again, there's multiple lenses, with the lenses being located close to the volcanic vent, which is the feeder dike that is feeding into this felsic volcanic center. You know, if we go to Laurent, same idea. This is the same kind of idea section that I showed you before. Down here is the outline of the massive sulfides that I showed you before. The volcanic structure dips like this. And now in yellow, you can see the outline of two felsic domes. And the domes are exactly along that volcanic structure, because that volcanic structure has controlled the hydrothermal fluid flow, but also the emplacement of these felsic volcanic rocks on the seafloor, right? And the massive sulfides kind of overlap and are in between these two domes. On surface, there's a really famous outcrop that you can see with these monomictic rhyolite breccias here that were originally glassy and have these pylitic cracks that formed in the hanging wall, that are on the stratigraphic hanging wall of the massive sulfides. You know, another example for vent proximity, a much smaller deposit. It's called the Potter deposit in Ontario. It's a very interesting deposit because it's located in ultramafic and mafic rocks. And it's one of the few deposits where the massive sulfides are hosted in volcanic rocks that have been deposited by a fire fountaining process. So that's what you see here, a volcanic vent. Then the lava comes out and basically erupts into the seawater, making this fire fountain, these bombs, and some of these bombs impact back on the seafloor and form these really funny shapes, including this dog bone, you know, this class that looks like a dog bone. There are armored lapellae and all these really interesting textures that you typically don't see because that is a very rare process. But the massive sulfides have formed within these deposits in proximity to the vent. Obviously, these bombs are not going to fly away very far from the volcanic vent. You know, here's another example where I've worked over the last couple of years in Ethiopia. This is an example where we can see what I mentioned before, peperites, intrusions of felsic volcanic rocks into carbonaceous mudstone. And it basically has intruded, the lava has intruded into that carbonaceous mudstone. And then the lava heated up the water, water in the pore space. The water in the pore space of this wet and unconsolidated sediment went to steam and ripped apart the lava, making all these funky shapes, very irregular bulbous clasts. And that is perfect evidence that the lava was intruded into wet and unconsolidated sediment. And that's about 100 meters away from a geophysical, was about 100 meters away from a geophysical anomaly at the time that the company Cuimont was looking at and considering to drill. And they didn't really like to drill it because it's in carbonaceous mudstone. And as you know, geophysics in carbonaceous mudstone is not simple. And because it was all on surface in carbonaceous mudstone, there was a lot of reluctancy to drill it, right? And to make an initial case to management to drill it, because obviously everybody knows that VMS are supposed to be in close spatial and temporal relationship to volcanic rocks. So if there's no volcanic rocks, there's no reason to drill. And then in this field work, we showed that there is a close spatial and temporal relationship because we have intrusions of these little rhyolite sills and dikes into the sediment when the sediment was wet and unconsolidated. And that was ultimately the reason why Cuimont drilled it. And they discovered a world-class deposit there in 2019. Unfortunately, at the moment, it's mostly in this part of the Tigray region where the civil war is ongoing. So I'm not sure how that's going to go in the next couple of years. Last but not least, we want to have alteration, hydrothermal alteration along our structures that go to the seafloor, because we have to prove that there is fluid flow up the structures. Here's an example from the modern seafloor that shows you how fluid flow will occur along structures. The fluid flow will organize into these finger-like upflow zones. So it's not happening everywhere along a plane. It's organizing into these finger-like upflow zones. And that's in fact what there's a computer model of how the fluid flow will occur. And that's what you can in fact see on the seafloor. So here's a mid-ocean ridge extensional zone, the location of the different massive sulfide lenses on the modern seafloor. And then here's a geophysical image that shows you where the basalt is altered, which means the magnetite has been converted into pyrite, meaning that it's demagnetized. And these are bullseyes, right? Demagnetization bullseyes in the upflow zones where our massive sulfides are, right? Obviously, the fluids come up and they alter the wall rock, and we can see that geophysically as an alteration footprint. We can see that geochemically. The Ishikawa Alteration Index has been around for a long time, and it basically measures enrichment in magnesium and potassium, which means chloride or white mica enrichment, sericite enrichment, and destruction of feldspars or glass, volcanic glass. Here's an example from the Norenda camp, a structure, a synvolcanic structure that was mapped out and is very well known in a 3D model. And then you can see drill core and geochemical analysis along the drill core. Look at that coverage. I mean, it's just crazy how much drilling there has been in the Norenda camp. But if you would take the whole geochemistry and contour this alteration index, you can see that that structure goes through the rock that has been hydrothermally altered. And the alteration halo around that structure drops off about 500 meters out of that structure. The alteration goes to background values. So this was one of the concepts that Xstrata at the time was looking at in the early 2000s to 2007s, and leading up to the discovery of a small massive sulfide deposit, because they basically looked at which structures were hydrothermally altered, or the wall rock around which structures were hydrothermally altered, and then they traced them in 3D going up to the favorable horizon and looked where there was insufficient drilling at the favorable horizon, meaning there's the ability to hide a massive sulfide deposit. And they hit the massive sulfides on the first hole, right, which is quite amazing, simply by 3D modeling, whereas the structure that has hydrothermal fluid flow intersecting the favorable horizon within a buffer zone that was not previously drilled. Massive sulfides on the first hole. And they won a pretty prestigious exploration award for that. Unfortunately, they all got laid off because the deposit they discovered was too small for Xstrata at the time. But they obviously all became really good and successful people in the junior sector. I guess what I want to talk about last is kind of the mechanism by which we are making massive sulfides on the favorable horizon, which brings us down to the deposit scale, right? We have identified big extensional zones, then we have talked about the favorable horizons, we have talked about some volcanic structures controlling fluid flow and seafloor volcanism, and we said we have to have alteration, we have to be vent proximal. So now we zoom into the deposit scale to figure out how the massive sulfides are exactly made and where exactly they are made. So first of all, here is an example of Australian deposits that was large put together in 2001 to show us the enormous variability in terms of shape and sizes of VMS deposits. And I always say to students when we go to the field, VMS deposits, every single one is different from the next one. And it always comes down to the permeability in the immediate subsea floor environment. Right? They're all formed by the same processes. So once you have seen enough of them, you kind of see the pattern. But when you're out there as a master's student or PhD student for the first time and you see the first deposit, you get totally confused because it's nothing like all the other deposits in the literature. Right? It's all about little permeability, local permeability controls. Just look at that, the Highway Reward deposit, it's a pipe in volcanic rocks. The Helier deposit, a very famous deposit studied by Bruce Gemmell for the most part, is a massive sulfide lens that has a carrot-shaped alteration halo. I talked about Thalanga before. It's a blanket-like deposit that is controlled by two synvolcanic structures. There's Rosebery in Tasmania, a very famous zinc-rich deposit that is hosted in pumiceous rocks and really as just a blanket-like sulfide zone. So they're all very different in terms of shape and sizes. I think one of the big revelations was when we looked at the modern seafloor, we obviously could see the black smokers because that's what we explore for, right? When we go to the modern seafloor, we try to find massive sulfides by measuring the turbidity in the water column. We have little laser instruments that measure the turbidity, and then obviously the more black smoke there is, so the higher the turbidity. That means the closer we get to a black smoker system. That means we actually have to have black smokers, and we have to get all the sulfide material particles out into the water column. However, that is super inefficient, right? This is a photo mosaic of one of these systems, and you can see for scale, this is a scale bar. This is a scale bar of 16 meters. You can see all these chimneys and the black smoke coming out of them. And if we cut them, if you take a sample and cut them in half, then we see the typical black smoker systems. Most of these little mounds are only about 5 million tons or less in size, which means they are certainly on the smaller side of the VMS deposits. That is the case for many of these deposits, including those of the famous Noranda camp, where the VMS, the massive sulfide lenses, are located exactly along these favorable horizons. So here are two of these favorable horizons stacked with little massive sulfide lenses that have formed where volcanic structures intersect these seafloor positions. And they have formed on the seafloor because the volcanic rocks on the seafloor are basically impermeable, massive andesites or basalts. And then the only permeability we have are the volcanic structures. So the fluids come up, they deliver the fluids to the seafloor along the structure. They quench and cool and make us a little mound on the seafloor. Then we have deposition of a new lava flow. Some of these volcanic structures are reactivated. We make a new massive sulfide mound and so on. All of these deposits are comparably small, with the Millenbach deposit being the largest one, that is about 4 million tons. Now, if we go to the modern seafloor, and I show you an example here from the Tyrrhenian Sea in Italy, we can see quite different relationships. So I want to take you here. This is in southern Italy. This is a subduction system where the Ionian plate subducts below Calabria and produces an arc here. This is called the Aeolian arc. And there's extension and a bunch of volcanoes. And one massive sulfide occurrence is located at Palinuro Seamount, which is about 650 meters water depth. We knew about the occurrence of massive sulfides there since the mid-80s, when there was a German research cruise that was scheduled to go to the Red Sea, and they are licensed to do research in the Red Sea in Saudi Arabian territorial waters was pulled as the ship was going there. And they really didn't know what else to do, so they basically went into Italian territorial waters because Germany has a pretty good relationship with Italy. And they just started sampling, dredging seamounts in Italy. And they actually recovered a bunch of massive sulfides from this Palinuro seamount. And at the time, obviously, there were no sophisticated tools, no images from the seafloor. We went back there in 2007 and in 2009. And this was early on in my scientific career. My very good friend, Sven Petersen, and we wrote a proposal to the German Research Foundation to go there and drill a hole on the modern seafloor to find massive sulfides because we knew it's there. And after our first research cruise in 2007, we did not see any massive sulfides on the seafloor. All we could see was that kind of stuff. Lavas, outcropping, sediments that were discolored, a bunch of bacterial stuff on the seafloor, and then these little mounds of tube worms that mean that there's low temperature hydrothermal activity. So we went there in 2007, took these pictures, and then we wrote a major proposal to get funding to drill on the modern seafloor, and that's obviously very expensive. So that drilling cruise was about 4 million euros. And we were very young and naive, and we didn't really understand what the heck we were doing. And then we went there and we drilled a bunch of holes. And luckily, we drilled massive sulfides. And after the fact, we were told by a bunch of the more senior people in Germany, like, well, if you would not have drilled massive sulfides, that would probably be would have been the end of your scientific careers in Germany, because you would have spent $4 million of taxpayers' money and not finding anything you promised to find. So we were kind of really lucky. But what happened there? So we drilled a bunch of holes, and drilling on the seafloor is difficult. So we could also only drill to about 5 meters below the seafloor. And we found massive sulfides in basically every hole we drilled, but as little as a meter away from the seafloor. So think about this. A meter below this is massive sulfide, right? We went back and measured temperatures. There's hydrothermal fluid flow coming through this sediment that is 60 degrees C here, 60 degrees Celsius here, and 1.5 meters below, it's 250 degrees C. So there is a very sharp temperature gradient in the subsea floor going from hot to cold, and it's shielded, it's almost insulated from the cold seawater by the sedimentary cover. Right, this is what the drill core looks like. There's essentially the silicified sediment, and below that we have massive sulfides, polymetallic massive sulfides and massive pyrite, the same way we would have it for a black smoker system in an ancient volcanic succession. But there's no outcrop, there's no black smoker. Why is that? Well, what does that mean? Well, it means that your massive sulfide forming fluids are cooling in the subsea floor rapidly enough to make massive sulfides before they get to the seafloor. So they form what we today call a subsea floor replacement deposit. They are not on the seafloor, they are forming by subsea floor replacement. So here's a bunch of textures as we can see them in drill core from the modern seafloor. Here's the sedimentary rock, and it's replaced from below by the sulfides, right? Or we can see breccias and textures like that. In fact, this was known or is known from the ancient rock record as well. Here's an example from Mark Hennington's study in Kidd Creek, where he showed us, this is now tilted in a way that stratigraphy goes up. We can see the top of the massive sulfide lens in Kidd Creek, and you can see that it kind of flares up into the volcanic breccias that are hosting the massive sulfides. Again, very strong evidence that the massive sulfides have formed by replacement of the host rock, not on the seafloor by black smoker activity. Same in the Horn deposit where I have worked. A lot of the sulfides, the massive sulfides, are formed by subsea floor replacement, and some of them have been redeposited into breccias on the seafloor. But many of these zones, this is a projection to surface, many of these massive sulfide deposits or lenses have formed below the seafloor, and the location of the seafloor is schematically shown by that line. So a large proportion of the overall endowment was formed by subsea floor replacement. Over the last couple of years, I have worked a lot in Peru. When I started working in Peru in about 2015, the Peruvians didn't really know much about VMS because they're obviously fantastic geologists in the porphyry and episomal and skarn environments, but they didn't really know much about VMS. Today we know a lot about the VMS in Peru, and there are some really spectacular deposits out there, including Palma and Cerro Lindo, that are Cretaceous in age, and they are located in these basins and these different basins of volcanic rocks, submarine volcanic rocks. All of these big deposits, Palma and Cerro Lindo, have formed by subsea floor replacement, and I just show you some examples of textures. So here the Palma deposit, much of the Palma deposit is in carbonaceous shales. You can see how the sphalerite replaces the shale and basically goes along bedding and replaces some of these shales along bedding planes. It almost looks like a ZX deposit, right? But it's a VMS deposit. It's contemporaneous to mafic intrusions into the carbonaceous material. Subsea floor replacement of a mudstone. Here's an example from Cerro Lindo, world-class deposit, 130 million tons by now. a zinc-rich deposit, breccia, volcanic breccia, rhyolite clasts, and then you can see all the sulfides infilling around the clast by subsea floor infilling and replacement. So this now seems to be the big topic in the VMS environment, that in many of these deposits, the world-class deposits, the big deposits, we have multiple ore lenses. That obviously is important to make a world-class deposit. And many of these lenses are formed by subsea floor replacement. As our high temperature fluids are getting towards the seafloor, they cool and quench in the immediate shallow subsea floor environment, producing these massive sulfide deposits. And maybe sometimes they get to the seafloor and make a plaque smoke accumulation. But we have to consider that many of the world-class deposits have a large proportion of the ore lenses to them that have not formed on the seafloor. Why is that so important? Well, because it makes it more efficient, right? If you can cool the liquid to 100 meters or maybe as little as a meter away from the seafloor and dump out all the sulfides, then you could have as much as 100% efficiency of dumping out the sulfides. If you make a black smoker system, then you lose 95% of the metal into the seawater. So here's the compilation from Jim Franklin that I mentioned before, from the 2005 paper and the SEG 100th anniversary paper. This is a great size distribution of VMS deposits. Out of the 800 deposits we have worldwide, about 500 deposits are less than 5 million tons. There's about 60 deposits that are more than 50 million tons. There's about 30 deposits that are over 100 million tons. Out of these deposits, I've probably visited about half of them. You can see replacement, subsea floor replacement textures in basically all of those ones that I've visited. So, and they are all, according to literature and my own observations, they are located in permeable stratigraphic host rocks where we can have subsea floor replacement. So that's kind of where I want to wrap it up for today, where I want to leave you as some of the ideas for geological criteria that we need in exploration. You know, I mentioned that we have to have crustal extension, and we have to have very rapid crustal extension that is followed by the VMS stage when we go into bimodal volcanism. We have to have one or multiple favorable horizons, and typically our VMS are not randomly distributed within the volcanic stratigraphy. We have to have subvolcanic faults that go to the favorable horizon, and obviously those will control where the fluids go, and they will also control where the volcanic rocks are formed, where we have vent proximity. We typically have a certain style of felsic volcanism. That's not necessarily the case for all VMS deposits, but for many of them. We obviously have to have evidence for fluid flow along the subvolcanic structures. If there's no alteration, there's no VMS deposit, because there's no fluid flow. And the big deposits, so most of those will have formed by subsea floor replacement, or at least will have a significant component of that to them. So I guess to wrap this up, I want to argue that being a good geologist is still very important, right? If we do exploration in the VMS environment, we do have to understand our rocks, we have to understand alteration, we have to understand structural geology. Field skills are still the number one, right? The geologist, the motivated explorationist with a really good understanding of the VMS model really is the best exploration tool we have. That doesn't mean that we can't make use of all these other techniques that are obviously important, like geochemistry and geophysics, but we always have to combine that with a really good geological understanding, which obviously is key. So this is where I want to leave you, or I guess, Corey, if you want to, we can entertain lots of questions. I think there's lots of VMS out there. This is Cerro Lindo in Peru. You know, Peru is now one of the top exploration places in the world to look for VMS, which is something we did not know about 10 years ago. And Cerro Lindo with 123 million tons of massive sulfides is now a world-class deposit, and it will probably catch up to Kid Creek by the time it's mined out. Okay, thank you very much.